Hello everybody, we're getting ready to do lesson 9.7 part 1, pre-calculus math today, classwork. And for today's classwork lesson, you got 4 points here on goes into your notebook guide. And then 40 points will go onto your classwork sheet, have those out in front of you, name, date, period. And homeschoolers and onliners, put your due date here. And we're going to start out with our bell work today, students, teachers. We have find the value of the trigonometric function given that u and v are in quadrant 4, u and v quadrant 4, u and v quadrant 4, and sine u equals negative 3 over 5, and cosine v equals 1 over radical 2. Cosine v is 1 over radical 2. So with those values, find the value of these trig functions here, 77, 78. Teachers, give your students about 5-6 minutes. Pause your video. See you in 5. Okay, everybody, welcome back for today's bellwork solutions. So we have cosine u plus v with these values of u and v. So for this one up here, cosine u plus v is the same thing as cosine u, cosine v minus sine u, sine v. And then when we plug in here, we come up with these values here for this function. And we end up with 1 over 5 times radical 2 will equal eventually radical 2 over 10. The 4 over 5 here, that's part of your cosine u here. Cosine u would be 4 over 5. And then cosine v here is 1 over radical 2. So knowing your trigonometric identities is crucial for this. And then same thing down here, sine u plus v, sine u cosine v plus sine v cosine u. And then when we plug in our values here again for 4 over 5 for cosine u, same thing as up here. And then when we multiply out, we end up with negative 7 over 5 times radical 2 is the same thing as negative of 7 radical 2 over 10 is what that will eventually come to. To today's classwork, we'll start with a notebook page here. In sections 9.2 and 9.3, you learned that the rectangular equations of ellipses and hyperbolas take simple forms when the origin lies at the center. As it happens, there are many important applications of conics in which it is more convenient to use one of the foci as the origin. In this section, you will learn that the polar equations of conics take simple forms when one of the foci lies at the pole. So foci are key here. To begin, consider the following alternative definition of a conic that uses the concept of eccentricity, which is a measure of the flatness of the conic, remember? So when we throw in eccentricity here, the alternative definition of a conic, the locus of a point in the plane that moves such that its distance from a fixed point, the focus, is in a constant ratio to its distance from a fixed line, the directrix, is a conic. So there's a great definition there of a conic right here. These two lines in this finish here. The constant ratio is the eccentricity of the conic and is denoted by E. Moreover, the conic is an ellipse where 0 is less than E less than 1, a parabola when E equals 1, and a hyperbola when E is greater than 1. So there's your definition there. Note that for each type of conic, the focus is at the pole. So here is a key word here, the pole. Note that for each type of conic, the focus is at the pole. Knowing that, so in this situation here, we have ellipse here, 0 less than E less than 1. PF over PQ is less than 1. So PF PF over PQ is less than 1, then we have an ellipse here. 0 is less than E, and E is less than 1. And then for a parabola, this would be a good summation here of what a parabola is. E equals 1. So when your E equals 1, you have a parabola. When E is less than 1 and greater than 0, you have an ellipse. So these would be ways that you can tell just by calculating your eccentricities. And then for a hyperbola, E is greater than 1. So when you have a hyperbola, which you have this situation here, you have a directrix here, and you have a directrix here, and you have a directrix here. So when your eccentricity is greater than 1, meaning PF over PQ equals P prime F over P prime Q prime is greater than 1, then you have a hyperbola. Okay, that is one way you can analyze which kind of conic you have from eccentricity. The benefit of locating a focus of a conic at the pole is that the equation of the conic becomes simpler. Okay, well, great. We're going to use foci here. So polar equations of conics, the graph of a polar equation of the form 1, r equals EP over 1 plus or minus e cosine theta, or 2, r equals EP over 1 plus or minus e sine theta. So we have the graph of these polar equations of these two different forms here. We have a cosine form, and then we have a sine form here. Is a conic where e is greater than 0. So in this case here, e is greater than 0, and the same thing up here, e is greater than 0. Is the eccentricity and the absolute value of p. Absolute value of p is the distance between the focus, the pole, and the directrix. So that's always going to be a absolute value here, the distance between the foci and the directrix. Okay, that's good to know. So an equation in the form r equals EP over 1 plus or minus e cosine theta, this would be a vertical directrix. So you have a directrix that's vertical oriented, corresponds to a conic with a vertical directrix, and symmetrics and the symmetry with respect to the polar axes. An equation in the form r equals EP over 1 plus or minus e sine theta will have a horizontal directrix. So it'll be horizontally oriented. So the sine's horizontal and cosine is vertical. This all corresponds to a conic with a horizontal directrix and symmetry with respect to the line theta equals pi over 2. So this is all key here with pi over 2 as your line of symmetry. Moreover, the converse is also true. That is, any conic with a focus at the pole and having a horizontal or vertical directrix can be represented by one of the given equations. So you know that with a horizontal, you have this situation here, and then with a vertical, you have this situation here. With different trig functions, your cosine is vertical, and then sine will be horizontal situations. And that'll tell you a lot right there, right up front. So identifying a conic from its equation, identify the type of conic represented by this equation here. So cosine here, we know exactly the orientation here, do we not? We do. To identify the type of conic, rewrite the equation in the form r equals EP over 1 plus or minus e cosine theta. So when we do that, we end up with this. R equals 15 over 3 minus 2 cosine theta. And divide numerator and denominator by 3. So we want to definitely get rid of divide numerator and denominator by 3. So we want to get rid of this here because we want to go into this form here. And to get to this form, we got to divide that by 3. If we do that, Now we know what we're dealing with. Because e equals 2 over 3 is less than 1, you can conclude that the graph is an ellipse. So we know it's an ellipse. Using the graphing utility in polar mode, and be sure to use a square setting as shown. This is our graph here now of the preceding expression there. We have an ellipse like this. R equals 15 over 3 minus 2 cosine theta. And then we end up with an ellipse like that. The graph of the conic appears to be an ellipse. It is an ellipse. It doesn't appear like it's an ellipse. It is an ellipse. Okay, so let's go into one here. Identify the type of conic represented by the equation, and then use a graphing utility to confirm your result. So our 15 here, which is our guided practice. This is our guided practice. This is yours down here, students. I expect you to do that and one on your own. So we have 3 over 1 minus cosine theta. And we know immediately, just by looking at it, that 3 over 1 minus cosine theta equals 1 in this situation. So we know it's a parabola. We know that much. So use the graphing calculator to confirm your results. Identify the type of conic. It's a parabola, okay? And this one down here, I'm going to let you do that, student. Moving on. So for the ellipse here, and this is the one that we did before, the major axis is horizontal. So here's our major axis here is horizontal. And the vertices lie at r theta, which equals 15, 0. 15, 0 is here. And r theta is 3 pi, which is over here. This is 3 pi over here. So the length of the major axis is 2a, which equals 18. We have 18 here as our major axis. 2a equals 18. To find the length of the minor axis, you can use the equations e equals c over a and b squared equals a squared minus c squared to conclude that b squared equals a squared minus c squared, a squared minus ea squared. So we have a squared. We factor out an a squared or 1 minus c squared. So this is your usual situation here for an ellipse. Break it down to that. Because e equals 2 over 3, you have b squared equals 9 squared bracket 1 minus 2 over 3 squared in bracket close bracket equals 45. Which implies that b equals radical 45, which is 3 times radical 5. So the length of the minor axis is 2b, which equals 2 times this, which is 6 radical 5. A similar analysis for hyperbolas yields b squared equals c squared minus a squared equals ea squared minus a squared. And then again, we factor out an a squared. We get a squared times quantity e squared minus 1, and then this would be a hyperbola here. Okay, let's try one now. So analyzing the graph of a polar equation, analyze the graph of the polar equation r equals 32 over 3 plus 5 sine theta. Dividing the numerator and denominator by 3, we got to get this to 1. Okay, divided by 3 produces 1 plus 32 over 3, 5 over 3 sine theta. Because e equals 5 over 3, which is greater than 1, we know that immediately the graph is a hyperbola. The transverse axis of the hyperbola lies on the line theta equals pi over 2. We know that as well. And the vertices occur at r theta, which in this situation here is 4 pi over 2. And r theta will equal, and by the way, here's our hyperbola here. R theta equals negative 16. So negative 16, which would be up here. Negative 16, 3 pi over 2. Because the length of the transverse axis in this situation here is 12, you can see that a equals 6. Since 2a equals 12, you know a equals 6. To find b, right, b squared equals a squared. times quantity e squared minus 1, and then when we plug in our values here, we have 6 squared, which is our a. 6 squared bracket 5 over 3 squared minus 1 equals 64. So b equals 8 in this situation here. B will equal 8. You can use a and b to determine that the asymptotes are y equals 10 plus or minus 3/4 x as shown. So 3 over 4x as shown. So let's try one here to prove this. In these exercises here, identify the type of conic represented by the polar equation. So here's our polar equation. And analyze its graph. Then use a graphing calculator to graph the polar equation. So we have a 14 over 14 plus 17 sine theta. And down here we have negative 5 over 1 minus sine theta. So this one here is problematic. So what are we going to have to do with that? We're going to have to divide through by r equals 14 over 14 plus 17 sine theta, which is the same thing, and we're going to divide through by 14 now. And by the way, this is 14, this is 14. That's kind of cool. So when we divide through by 14, we have e equals 17 over 14, which is greater than 1. So we know this is a hyperbola here, just by that. Then use a graphing utility to graph the equation. And then here would be the graph of this polar equation here. Once we plug that into our calculator, you'll find that this is the way your hyperbola will be. And that is your 9.7 part 1 pre-calculus math classwork. Email me here, animatedpowerpointmathvideo@aol.com, for questions, materials, and other situations. Thank you very much.